Well, good afternoon, Year 12. So I'm really sorry that I can't be with you today to do our live lesson, but we've had a few technical difficulties on the school side. So I've got the ability to record at home, so I thought that would be the best thing for me to do. So this slide says Introduction to Halogens. Obviously it should say Halogenoalkanes. I have no idea what I was thinking about. But just to prompt you that I would like you to be in the lobby 3 or 4 minutes before the start of our class time so that I can let you in. I'll have a little bit of a notice screen like this, maybe with some shout outs on it, but it does mean that I can start promptly on time rather than letting you in 1, 2, 3, 5 minutes after the lesson. So whilst your class is not a problem, it's starting to become an issue across the school, so I thought I would just put that expectation out there that you need to be 3 or 4 minutes before the lesson start time waiting to get in. So a big puppy thank you to Sharina, Grace, Georgia, Phoebe and Nathan for turning in your ozone research task early. I've had a look on our class notebook, I can see it there, so thank you very much. And it's just a gentle reminder to everybody else that that assignment is due this week, so please make sure it is done and it's uploaded and turned in so that I can review it. If you've got any issues on how to turn it in or how to upload it, then just drop me an email and I can talk you through that process. Okay, so let's get to our lesson with the correct title on the slide now. So it's Halogenoalkanes. So here you've got your spaced retrieval. Please pause the video now, spend about 5-6 minutes on the spaced retrieval, and then you can move forwards and get the answers. Okay, so this is our check. So the first one was fluorine was a radical, water wasn't, and the methyl was a radical, and that's because they have a single unpaired electron. So which atom contains the radical? Well, obviously fluorine is the atom, water doesn't have one, and in the methyl it's the carbon that contains the radical. Okay, so draw the skeletal formula of the following. So that's basically the line drawings, and this is what they look like. So you've got dichloromethane, the iodopropane, or 2-iodopropane, and then the dichlorobromoethane. And then the house science work question. Oh, sorry, they're the answers. And then the house science works question. If you were going to do a Google search, why wouldn't you trust the information? The reason is it's open access and anyone can change those pages. So you'd really need to cross-reference the information with a more reliable source. Maybe if you're looking at chemistry, the Royal Society of Chemistry or the Royal Society, a university web page, or you would consult an expert. I consider myself quite knowledgeable, and so when I read things on Wikipedia, I sort of know if it doesn't ring true, and so I can then look at a different source. So having the wider knowledge sometimes helps you, but just to be aware, it's open source and other people can edit. So you can pause this and get the answers. Make sure you green pen and correct. I will be asking you to just send me a copy of your work, just to take a photo of it and send it to me so that I can see it's been done. Okay, so why are halogenoalkanes so important? So from crude oil, we fractionally distill crude oil, we get the different alkane fractions, and we react them to give us, by radical method, you had a look at that already, to give us these halogenoalkanes. They're the starting materials. This is how we get crude oil, which is fairly unreactive, into a state where it will undergo chemical reactions. And so those halogenoalkanes are the source material for a lot of things. Medicine, expanded foams, polystyrene cups and things. They go into aerosols and into refrigerants, lots and lots of areas. And your ozone research may very well have given you information on what contributes to the depletion of the ozone layer, so you would get some of that information. Okay, so the importance of them is they are a valuable source of synthetic compounds. So synthetic means to make, so they're things that we make, and they're the starter materials. Alkanes, very unreactive, so we need to react them, we need to make them reactive, and we do that by creating these halogenoalkanes. So they are a valuable source of other things. So they're only made of one type of compound, so that and they are made directly from alkanes. And the halogen atom can easily be replaced. The reason it's there, it does create a reactive carbon that will accept incoming species, and that halogen will just drop off, or not drop off, but it will leave quite easily. And we'll look at the bonding and the bond strengths to see why this is the case. So what's our learning? We're going to look at nucleophilic substitution. I'll talk about that a little bit later on. As we're going through the slides, there's quite a bit of vocabulary that you need to make a note of and you need to write down, so definitions. So don't just skip past. Please make a note of them, because we're going to come on to them time and time again. So you can pause the slide and you can have a look at the goals. Today I'm going to be talking about polar bonds and homolytic and heterolytic fission, and I possibly will get to nucleophiles, and I'm not necessarily going to talk about nucleophilic substitution. We'll just see how we get there. So pause the slide, have a look at what we're going to do, restart when you're ready. So there are several different types of halogenoalkanes. There are homologous series. So homologous, I did a little bit of research around this, and I can split it up into homo and logous, but actually homologous as itself means it's something that agrees, or it's of the same mind, or it's equal. But in terms of people and groups, so you've got a group of people that are of a similar mind, or you've got a group of objects that are similar, and they agree, or they're fairly equal. So a homologous series is a family of compounds that undergo the same sorts of reactions. They have the same types of properties. So we've got the various halogenoalkanes. We've got just ones that have been chloro substituted, so the chloroalkanes, bromoalkanes that have got bromine in them, the iodoalkanes that have got iodine, and fluoroalkanes. You've come across mixed halogens, and as I say, they're all homologous. They're a homologous series. So this is just a recap on the naming conventions. So you base the name upon the corresponding alkane. So we name from the base alkane. We find the longest chain. We then, because it's got chloro or fluoro or bromo in it, we prefix at the front. We prefix chloro or bromo. So bromoalkane, bromomethane, and that has to be done in alphabetical order. So we name it on the halogen. Not whether there's 2 or 3 or 4 of them, but on the halogen itself. Then we count up what number carbon the halogen is on, and we try and make it the smallest number possible. So we count from the shortest end of the chain, so that the halogen comes with the lowest number. So it'd be substituted on carbon 2 or 3 rather than carbon 7 and 8 at the other end. So it's the smallest number. And then we use the prefixes di, tri, tetra, which is 2, 3 or 4, if there's a multiple of the halogen. So it's alphabetical order in terms of the halogen, and then we put di, tri and tetra in front of it if we've got 2, 3 or 4 of those chloros. Okay, so this is in your booklet, so you can complete this in your section of the booklet, or you can do it on paper if you would like. So I'm going to leave you, pause the video here, complete that, and then we can move on to the next slide. Okay, so here are the answers then. So you can see we've got chloroethane. I've drawn out 1,2-dibromopropane. I've kept it in the same with the same structure as what was previously shown, so I haven't drawn it as a skeletal formula. And the two challenges at the bottom are shown. So just check that your answers are right. Use your green pen to amend and to add to your notes. Okay, so with our alkanes, or halogenoalkanes, we have a way of naming or identifying the type of carbon that they're on. So you can see here we've got something called a primary, a secondary and a tertiary halogenoalkane. Well, what does that mean? Well, the halogen, which we represent as X here, is the halogen, and you can see it's attached to a carbon, and we look at what else is on that carbon. Now the R group, I'll come on to naming to the conventions of the R group, but the R group just represents an the rest of the alkane, so typically that would be a carbon. So there's only one carbon attached to the carbon halogen there's only one carbon attached to the C that contains the halogen. So that's what we call a primary substituted halogen. So it's got two hydrogens and a carbon and a halogen. So it's the fact that it's got one carbon attached to the carbon of the carbon halogen. If we look at the secondary group, then you can see if R is a carbon chain and an alkyl chain, and the other R is another alkyl chain, you can see that actually that carbon halogen position has got two carbons attached to it, two carbon chains. So there's two carbons attached to the carbon that has the halogen. So we call that secondary. And then in the tertiary substituted one, the carbon that contains the halogen has got three carbons attached to it, three alkyl chains sticking off it, if you like. So we call that tertiary. And you can see the way that we would write them, one with a little superscript naught and a line underneath it. Don't ask me why, but that's the way we do it. So these are primary, secondary and tertiary. If you need any other assistance in that, you can see the link at the bottom to another web page, although I would suggest that you go to ChemGuide, because that is pretty good if you want additional information. So again, check through your notes. This should be in your booklet. If it is, just add a few of your own notes next to it. So do that now, pause the video and just write it so that you understand it. Okay, so here we've got some more compounds, so examples of what a primary, secondary and tertiary haloalkane look like. And you can see with the first one, 1-bromobutane, the carbon that contains the bromine only has one other carbon on it, and so that's primary. In the 2-bromobutane, you can see that the carbon that contains the bromine has two carbons attached to it. One's a methyl group, one's an ethyl group. And then in 2-bromo-2-methyl propane, it's tertiary, and the carbon that contains the bromine has got three other carbons attached to it, three methyl groups. So that makes it tertiary. This is really important when we come to looking at speeds of reactions. So it's important that you memorize these and commit them to your memory and make notes in your book, because we're going to draw upon this in when we do what's called organic synthesis, when we use all the reactions that we know to make new compounds, these are deciding factors for us. So really important. So what 3 facts can you deduce from this table about the halogenoalkane? So I would say pause the video now, look at this and give me 3 trends. That's what I'm looking for, 3 trends. So see if you can identify the 3 trends. Once you're happy, then you can start the video again. Okay, so if you wanted a haloalkane with a higher boiling point, what would you do? Okay, so the trends you picked out, could you answer that question? If not, pause it and reconsider. Okay, if you wanted a halogenoalkane with a high boiling point, how could you change it, or how could it be changed so that you would get a halogenoalkane with a higher boiling point? So this is looking at the trends. Okay, so if we look at the top 3, they're all methyl halogenoalkanes. So we've got fluoromethane, chloromethane, bromomethane and iodomethane. Let's look at the boiling points. We can see the boiling points increase. So as the mass of the atom increases, as you go down the halogen group, the boiling point increases. Okay, so if I wanted a higher boiling halogenoalkane, I'd add a heavier halogen. So I would go from fluorine to chlorine or bromine or iodine. Okay, so that's 1 fact. I need 2 more. So if we look at the green spots now, so I've got chloromethane, I've got dichloromethane, and I've got trichloromethane and tetrachloromethane. And if we look at the boiling points of those, you can see that the boiling points increase. So as the mass increases, the boiling points will increase. But basically, as the number of chlorines on the species increases, the boiling point increases. So there's our second trend. So we're comparing like with like. So think back to making it a fair test. We're not comparing apples with oranges, so to speak. Okay, and the third fact then. So if we look at the single chlorine species, so we've got chloromethane and we've got chlorobenzene. That's what the bottom one is, benzene. And you can see that the boiling point will increase as the mass of the compound increases. So whilst we've kept the chlorine the same, we've got 1, we've changed that group then on the side. So we've gone from a methane group to a benzene group, which is a much bigger atom. So increase in the mass will also increase in the mass of the group will increase the boiling point as well. So you need to make sure that you write that down in your notes so that you understand that, because again, these are questions that will be asked, and when you're using this later in the course, then you'll understand. Okay, so I'm going to look at some bond breaking, and then we're going to just investigate one. So there's 2 types of 2 ways that we can break a bond. I'm going to just clear that out of the way. We can break a bond by breaking down the middle, and like in our radical reactions, the chlorine will take its electron with it, and the methyl group, the carbon, will take its electron with it. So they share that electron equally. That's called homolytic fission. And so this is where the vocabulary comes in. Homo or homeos is the, I think that's how you say it, is the Greek for equal. So heteros is different. And lytic we always think of as breaking apart, but that comes from lucis, which means loosening. So homolytic fission is an equal breaking of that bond. So we make two radicals, and we've covered those radical reactions previously. You covered those with Miss Priest. So another way to break the bond is that one of the atoms takes both electrons. So as you can see here, chlorine has taken both electrons. It satisfies that it's got a full outer shell, but it does mean that carbon has lost its electron. If the electron it was sharing has gone, it's gone to chlorine. So it is now positively charged, or it has a formal positive charge because it's lost its electron. And because chlorine has gained that electron, it has, thank you. And because chlorine has gained that electron, it's become negatively charged. I meant to pause it there, and I obviously haven't. I paused the share, I didn't pause the recording. Oh well, hey ho. Right, so let's move on then. So we are breaking bonds. So there's two ways of breaking bonds. So make sure you have drawn and made a note of this. And this is called heterolytic fission. So we've split that bond not equally. Okay, so I want you to pause the video and I want you to consider this graph that shows the bond strengths between carbon and the different halogens. So as you can see, the bond strength falls from carbon fluorine to carbon iodine. So that's suggesting that the carbon fluorine bond strength or bond is much stronger. Well, it is much stronger, but much stronger by a bit. You can see that the bond strength is just falling off a little bit between chlorine and bromine and iodine, but it falls off quite a lot between carbon and fluorine. So that is because it's a very strong bond. Okay, so which halogenoalkane is going to be the most reactive and why? So pause the video here, and this is where you can make your prediction. Which is the most reactive? Well, it will be the carbon iodine, because that you don't need much energy to break that bond. So because you're not using much energy to break that bond, then it will be much easier to break, and so it will be the more reactive. So let's have a look at the influence of bond polarity. So fluorine is very electronegative, and iodine's the least electronegative of all the halogens. And when we look at who has the greatest, or which has the greatest share of those electrons, when we look at carbon fluorine, it's fluorine. Fluorine has the greatest share of those electrons, and it's also got the so as a consequence, it's got the greatest distribution of partial charges. So there's a huge amount of partial negative charge on fluorine, which means that the carbon will be hugely partially positively charged. When you compare them to, say, chlorine or in fact bromine, the partial charges get less, so the difference between those charges is less, because the electron is not over towards one of the atoms now, and it's starting to come into the middle until we get to iodine. And the carbon and iodine have similar electronegativities, so that electron is shared more or less equally in between the two, between carbon and iodine. So the question is, it might be a trick question this, which halogen is going to be the easiest to remove by heterolytic fission? Heterolytic. Okay, and why? Okay, so pause, have a think, write it down on a scrap piece of paper, And then let's have a look at the answer, or at least my hint anyway. Did you consider the bond strengths that you learnt just on the previous slide? What do you know about the bond strengths? Because that will tell you which will make the easiest, which will break the easiest. So I guess it was a bit of a trick question. Whilst the electrons might be pulled over to fluorine because it's got the greatest electronegativity, actually the distance between fluorine and carbon is quite small. So the interactions, the attractions, if you like, are quite strong. So yes, fluorine does have the greatest share of the electrons, but actually the charges are very close together, which makes it very strong. Whereas in something like bromine, whilst bromine has some of the electrons, those atoms are quite a long way away, so the forces of attraction between them are much less. And then when we get to carbon and iodine, the electrons are in the middle, and because of the size of the iodine, it's quite large, the carbon's going to be quite a long way away from the positive attraction of the nucleus. It's going to be quite a long way away from the centres. When you measure from the centres, are going to be a long way away, so the distance is huge. So the interaction you've got is really those electrons holding them together, because the electrons, they get shared between the two atoms. So is that what you'd said? Don't tell me you said that the carbon-fluorine bond was going to break because the electrons are towards it. Okay, classic mistake if you did. What I want you to do is to now take some time to summarise your learning of heterolytic fission of the carbon-halogen bonds. So I want you to comment about the bond strength, so that's why I've included that bar chart, and I want you to talk about the polarity, the electronegativities and the polarity, and what we just described on the previous slide. So take 3 or 4 minutes to write, I would say about 4 or 5 sentences to summarise this information. Okay, so reactions involving heterolytic bond breaking. So we're going to talk about curly arrows, and I know Miss Priest has started to use them. These are called curly arrows, and we use them. It's called mechanisms. It shows us how electrons move, and when I was at university we used to call it pushing the arrows. We used to push the arrows, but I'll talk about that convention later. But suffice to say that what it shows is that the bottom of the arrow shows where the electrons are in a bond, and it shows where they're going to move to before they move. Okay, and then after our reaction arrow, those electrons have moved and the bonds have broken, or the bonds have been reformed. But I will go through that in a later lesson. If you want to find out, then you can always YouTube it. Okay, so this is heterolytic fission, and we can see that we've got the chlorine taking the extra electron, so it's now become negatively charged, which means carbon is without its electron that it shared, so it's positively charged. It's a positively charged species. It is an ion. So looking at this, what does this diagram actually mean, and what kind of species would be attracted to this type of carbon atom? So we're looking at the carbon atom. Okay, so it's the carbon atoms that make and break bonds. Okay, so what does that diagram mean? So in your head, rehearse that. And what species are attracted to the carbon atom? Again, in your head, rehearse that. So what we see is this diagram is showing us bond polarity. It's showing us that the bromine has got the greater share of the shared electrons. So it's attracting the electrons more towards it than carbon, and so as a consequence it has more of that negative charge. So we use the delta negative, which is it's slightly negatively charged, and as a consequence carbon has lost its share, if you like. So it doesn't see its electron in the same way. So it becomes slightly positively charged. So delta plus. So we do call it delta minus and delta plus, or delta positive and delta positive and delta negative is how we say that. So delta positive and delta negative. I'm going to talk about nucleophiles. So we need to know what nucleophiles are. So philos comes from the Greek word for love. And a nucleophile is a nucleus-loving species. And we know that nuclei of atoms are positively charged. So a nucleophile is something that likes a positive charge. So it's looking for a positive charge. So a nucleophile is an electron pair donor. Okay, so it's going to donate its electrons to something that is more positively charged. So you can think of coordinate bonds when those two electrons are donated to an area that is slightly more positively charged. So a nucleophile is an electron pair donor. It donates an electron pair to somewhere that is without enough electrons. So it's going to be slightly positively charged. So nucleophiles are things like a cyanide ion. So cyanide is C triple bond N, and the formal charge is, it's formally charged as -1. So the cyanide ion. And then we've got the ammonia molecule, and that's got a lone pair of electrons. Well, so is cyanide actually. And then the hydroxide ion has a lone pair of electrons. But you can draw these out. You can do the box notation. You can then do the sharing of electrons, and you can work this out. So cyanide ion, ammonia ion, hydroxide ion. There's the three we're going to be looking at. So again, make a note of those. Right, so I'm going to change my camera, and I'm hopefully going to give you a demonstration of heterolytic and homolytic fission. So perhaps I'm not. I'll pause the video and I will do that. Okay, so here's my molecule XY. Here's my covalent bond between them. So these are the two electrons. And so I can break this bond in a homolytic fashion, and I'm going to get two species, and one of them is going to have the electrons and the other one isn't. So I'll just do that now. Okay, so when I break the bonds, and if X takes the electron, as you can see here, it has an extra electron, so I've given it a formal negative charge. I put a circle around it so you can see, and you can see here that these are the two electrons in the bond. So X has taken those electrons, so X becomes negatively charged, and Y has lost its electron. We can see here it was sharing its electron, but now Y has lost his electron to X, so Y becomes positively charged, and I've put it in a circle so that we can see that. So we have these two separate atoms. Okay, so let's have a look at a different way of breaking the bonds. So if we break the bonds so that Y has the electron and X doesn't, we can see that the electrons have gone over to Y, so the shared electron from X has gone to Y, so that means it's gained an electron, so it's gained a negative charge. So I've shown that formally as a negative charge in a circle. And because X has lost its electron, in effect it's becomes positively charged, so I've put that in a circle as well. On both of these sides we've got a neutral species, and we balance out the fact it's neutral here by one species has to be positive, one species has to be negative. So when we combine those charges, overall there's a neutral charge. similarly down here. But if you look at it in terms of the electrons moving, then you can, in your head, you can see why that would be the case. So here, X and Y, they share an electron each. They would have been neutrally charged, and then they shared their electrons. And then if one of the electrons is lost to the other species, as in this case, Y will have that share and become negative. X will have lost its share and become positive. So there's two ways of breaking a covalent bond, and it depends a lot on the electronegativity of the group that we're looking at, and the bond strengths as well. Okay, so when we're looking at chemical reactions, then heterolytic fission is a type of fission where ions are formed due to the breaking of a covalent bond, and I showed you that on the demonstration. So usually a single bonded molecule will break, and it'll form two ions, one of which is a cation. That's a positive ion, so we use that terminology, cation, positive ion, and the other one is an anion, a negative ion. So again, if you've not come across cation and anion before, please make that part of your vocabulary, because you will be hearing it quite a lot. Okay, cations, positively charged ions, anion, negatively charged. And just the demonstration that I showed you, that's how we would write it in written form, just to show that we can get a heterolytic bond fission and we can get two different types of ion. It can break in two directions. Okay, so it says in the back of your books, but actually just in your books, what is a halogenoalkane? Explain why halogen carbon bonds are polar. What's a nucleophile? Give two examples of nucleophiles that will react with halogenoalkanes, and what does a pair of dots represent on a nucleophile? So if you can answer those questions, I've actually got this as a Microsoft Teams quiz. So I'm going to stop the recording now, and if you can make the notes and take that quiz, that would be very much appreciated. So as I say, I'm really sorry that I've not been able to get to the lesson today, but I do hope that this live recording, with all the issues that I've had, has brightened your day. Okay, so I'll stop recording now, and I look forward to seeing your work. So once you've done this work, just take a photo of it, and you can upload it to your area of the notebook, create a new page for it, and call it today's lesson, and put the date on. Okay, thanks very much. Bye-bye.